All right, we're going to start 5.3, and in 5.3, we're going to actually be looking for solutions for differential equations that are higher order, but where the coefficients are all constants. It gets a little bit more complicated if you had functions of x in front of these, um, and we'd have to look for other solution methods, but if it's constants, we can handle it. And all we're really going to do is extend things we've done earlier this year. Earlier this year, if we had a first order differential equation with constants in front, all we really did was figure out what the roots were, what the zeros were, and then our solutions were just CE to the whatever that zero was times x. Then in 5.1, we looked at second order differential equations where there were constants in front, and we looked for the zeros or the roots of a quadratic equation that used those coefficients. And if the roots were unique, if we had two different roots, then our general solution was just c1e to the first root times x plus c2e to the second root times x. If we had a repeat root, so if you had the same factor squared, then we had to put an x inside of there so that these would be linearly independent. If they weren't linearly independent, then our solution fell apart. We looked at that in 5.1. Now, the thing we did not talk about is what if they're imaginary? We'll leave that for another day. We'll get there. So, piece one, what we're going to focus on today is what if we have distinct roots when we're looking for a higher order differential equation? Well, just like we did with the quadratic, we are going to set up now a big polynomial. And as long as the roots of that polynomial are all real numbers and distinct, meaning we don't have any repeats, then our general solution is going to be like that quadratic. It's going to be c1e to the first root times x plus c2e to the second root times x. And however many roots we have, if we have 10 different distinct roots, you're going to have 10 pieces, and you're going to have a constant times e to the root times x for each one of those pieces. If you looked separately at e to the root 1x, e to the root 2x, because those roots are all distinct, if they are different values, then those functions would be independent, and that means that we have a basis for our n-dimensional solution space. However many different roots you're looking at, that would be the dimension of your solution space. So here we have a third order differential equation, and the coefficients of each of the pieces are constants. We have a 1, a 3, a negative 10, and technically a 0 on the y. So the characteristic polynomial that would match up with this would be r to the third plus 3r squared minus 10r, you could put plus 0r, equals 0, but we don't really need to do that. And this will be such a fun blast from your past. This is just finding roots of polynomials. So we would factor out an r, that would leave us r squared plus 3r minus 10 equals 0. And we can factor that quadratic a little bit further into r plus 5 and r minus 2. So then our roots would equal 0. So then our roots would be r equals 0, r equals negative 5, and r equals 2. Since they are all real and they are all distinct, our general solution then would be y equals c1 e to the 0x, technically, plus c2 e to the negative 5x, plus c3 e to the 2x, but we probably would just leave that first one as c1 plus c2 e to the negative 5x plus c3 e to the 2x. And you wouldn't have to write that step if you just want to jump right from there to the end. That would be just fine. And that'll be it for today. Let's do a little bit of practice of that in the homework, and we'll call it good.